All right, so part one, video review of graphing the natural log function. So the definition of a natural logarithm is that the natural log of x is equal to b if and only if e raised to the b power is equal to x. And remember, e is approximately 2.718. It's just a constant, okay? It's our natural base of e. So what this is really saying is that natural logs and exponential functions are somehow related. And the relationship is actually going to be that they are inverses, which we'll go over again later. But the natural log of x is equal to b if and only if, remember this has a base e to the b is equal to x. All right? So it says try on your own, but I'm going to help you through it. Graph y equals the natural log of x. Also fill in a table of values for -1, 0, 1, 2, and 3. So go ahead and grab your calculator if you don't already have it. We're supposed to fill in for -1, 0, 1, 2, and 3. All right, so I'm grabbing my calculator here. And let me clear out all the other stuff we had in there. Try to clear out all the other stuff we had in there. Clear, clear, clear. Great. Okay, so looking at our table of values that we are trying to fill in, the most efficient way to do this would be to go to y equals, type in the natural log, which is over here on the left, and go ahead and go to our table. I want to know -1, 0, 1, 2, and 3. Okay, so there's your values that you can go ahead and write in. We've got error, 0, 0.693, 1.099. 0.693, 1.099, error, 0. So we're supposed to graph this thing, which again, you could look at your calculator, but I'm going to plot these points that we have. We have 1, 0, we have 2, 0.693, and we have 3, 1.099. So what ends up happening is that the error is coming about because we cannot take the natural log of 0. We're going to talk about why that is in just a minute. But our graph ends up looking like this. So here's our table that's nice and filled in. Key features of this graph. We have a vertical asymptote at x equals 0. We have the point 1, 0. And then if you look here, we cross over 1 at a number that's somewhere between 2 and 3. Well, that number happens to be e. So key features of the graph. Vertical asymptote, the point e, 1, and the point 1, 0. Because the natural log of e is equal to 1, and the natural log of 1 is equal to 0. And let's look at why that is. According to our definition above, I'm supposed to be able to take this base and rewrite it. E to the first is equal to e. Yep, that's true. I'm supposed to be able to take this base, e to the 0 is equal to 1. Yep, that's true. So those two facts are checking out for us. Now, it's true for the natural log of e being equal to 1. It's also true that the log base 5 of 5 is equal to 1, or log base 10 of 10 is equal to 1, log base b of b is equal to 1. So what ends up happening is that we will always go through the point our base, whatever it is, 1, because of that definition. B to the first is equal to b. 10 to the first is equal to 10. 5 to the first is equal to 5. All logarithms, regardless of their base, will go through the point 1, 0. Because whatever this base happens to be, when you take a base to the 0 power, you end up with 1. All right, use the graph in the table above to graph this function. So thinking about this, we are going to take our graph and we're going to shift to the left 2. So I had a vertical asymptote at 0. Now my vertical asymptote is going to be to the left 2. I was at the point 1, 0. I'm going to move to the left 2. I was at the point E1. I'm going to move to the left 1, 2. And I'm going to reconnect my natural log function. Natural log of x plus 5 just moves the whole graph up 5. So my original graph, again, vertical asymptote was at 0. And if I take that vertical asymptote and I shift it up 5, well, it's still at 0. The point 1, 0 is now going to be up at 1, 1, 2, 3, 4, 5. And the point E1 is now going to be up at E1, 2, 3, 4, 5, 6. So we'll have shifted up 5 units. So there's the one that's up 5. The last one then is going to be a vertical stretch of 2. Well, if I vertically stretch my asymptote, it still is going to be 0. Now instead of the point 1, 0, I'm going to go 1 and then 0 times 2, which is, well, still 0. Instead of going over E1, I'm going to go E over 1, that's multiplied by 2, so now I'm up here, and we can see this vertical stretch happening of our natural log function. Something to be careful of on your calculator. If you are in a Zoom 6 scenario, your calculator makes it look like the natural log stops when it gets close to 0, almost like a square root swimmer's arm thing. But this extends all the way down. It's just that you're getting infinitely close to that vertical asymptote. All right, so some properties of the natural log function to always be aware of. The domain is x is greater than 0. We also could write that as 0 to infinity. You may not take the natural log of 0, because if we tried to do that, the natural log of 0 equaling some mystery, that would mean that e to the x is equal to 0. But the exponential function has a horizontal asymptote at 0. This is never going to be true, which means the natural log of 0 is never going to be defined. The range is going to be all real numbers, which would be from negative infinity to infinity. This function is continuous, increasing, and 1 to 1. So 1 to 1 is a function where for each y value, there was only one x value in the domain. So an example of something that's not 1 to 1 would be a parabola. Because a parabola, for the output of 4, for a y value of 4, you could have had an input of 2 or an input of negative 2. So that would not be 1 to 1. But our natural log function is 1 to 1. And this graph is always increasing, which means that the derivative of the natural log of x is going to be positive. Continuous means we should be able to draw without picking up our pencil. And this graph will always be concave down, which means the second derivative is going to be negative. All right, there's your properties of the natural log function and understanding its graph. So please make sure you understand how to work with logarithms and the definition.